Dr. Pfeiffer, I had sent you a little direct message.
Does it need to be something discussed in private?
Yeah, I just told you I had sent you an email regarding the test and me just having access to McGraw Hill. So that was it. But I don't think it'd be
You-
not a huge
I mean,
problem.
are you able to access it?
I just been able to because I was sold a book and the access code wasn't working. And I have proof of it all from the bookstore, but I was able to access it a couple of days ago. But I've been working on
Yeah,
it's just
that's fine.
I'm just
As long as you're working on it and you get the thing submitted before the end of the semester, then you're fine.
okay, so you can still work on tests after the late due date. That's my only question.
Yeah.
All right, bet. Thank you.
Uh-huh. Let me see. We're just about ready to get started, gentlemen. Just still kind of getting set up here. So I got students trickling in. I think we're good there. Let these gentlemen in. I'm gonna go ahead and get the party started. Oh, I think I got these gentlemen. Okay. Let me see something. 11. This student. I'll check back. I'll check attendance again in about 15 minutes, give or take. All right, let me go ahead and share my screen. Okay. All right, so we'll start here. Let's see. Okay. All right, greetings, scholars. So let's see. I think we just took exam one, so I'll you can anticipate seeing your grades within about a week. Do we have spring break next week? Is that next week? I think we still got 2 weeks until spring break. Is that correct? This is week 7. Let me check
We
something.
got 1 week till spring break.
Is it next week or
No,
week
it's
after?
not next week. It's the week after
Yeah,
that.
week after next. Yeah, that sounds right. Yeah. So um yeah, so you can anticipate your grades just within about a week or so. Um, it's just takes a little time. Let me see. Okay, so I can't think of anything. So we're going to be moving into chapter 3. Okay. So let me see. We've talked about, like, we've introduced derivatives. Again, derivative is a slope of a tangent line at a point. We introduced the concept of derivative with the limit definition, the limit definition of the difference quotient, and then after that we started exploring just techniques for finding the derivative. And so you'll see how all that work we used to do to find a derivative would take up a whole page. Now with some of those techniques, we can just look at the setup and just pretty much write the answer. A lot of those techniques. What else did we do beyond that? Then I think we got into like a few applications. And I think we got into higher order derivatives. So we're gonna kind of let's see. I think we're gonna kind of continue that discussion. So chapter 3 are applications of differentiation. All right. So now we've explored like the backstory behind the derivative, and then you know techniques on finding the derivative. So now we're going to look at some applications. So now we're going to use a derivative to kind of just explore some of the ways it can be applied. So we're going to start with section 3.1, using first derivatives to find max and min values and sketch graphs. As usual, if you have questions about anything, feel free to unmute yourself to get my attention. And this is one of those like accelerated weeks. We need to do like 2 sections a day and 2 sections on Thursday. I think that I think after this week, though, I think the rhythm slows down. We get down to like 1 section a day. So it's not too many more of these 2 a days. It does start to slow down in the near future. Okay. As far as the rhythm or the rate. A few objectives here. Find relative, and this is a long section, so we'll do the best that we can. Find relative extrema of a continuous function using first derivative test, and then sketch graphs of continuous functions. So function f is increasing over an interval I if every a and b in I. If a is less than b, then f of a is less than f of b. Graphically speaking, like if we were looking at the image, as we trace it left to right, the graph is going to go up. That's essentially what that's saying. And then there's a similar narrative for when f is decreasing. Really, just that concept of the graph is all you really need there. So let's see. So let f be differentiable over an open interval I. If f prime is positive, for all x on the interval I, then f is increasing over the interval I. So conceptually, what they're saying is like, no matter where you find a derivative of the function over that open interval, if the derivative is always positive, having a positive slope, then that's saying that the original function is increasing over the interval. All right. If you have the open interval I and the derivative is negative for all x in the interval I, then f is decreasing. Right. Again, the derivative being the slope of the tangent line at a point. So if all the points on the open interval, the slope is negative, then we say the function is decreasing over the open interval. A critical value of a function f is any number c in the domain of f for which the tangent line at c, f of c, is horizontal, or for which the derivative does not exist, right? So now we're kind of using derivative. If our derivative is positive, that means our original function is increasing over that interval. If our derivative is negative, that means the original function is decreasing over that interval. And then the critical value is going to be where the derivative is either 0 or does not exist. So that is, c is a critical value if f of c exists, and if f prime of c is 0 or f prime of c does not exist. Okay? If c is a critical value of a function f, then c f of c is going to be the critical point. Okay, so essentially what we're doing, we are using the derivative to start to explore like graphing techniques. In college algebra, we had several techniques that we applied, like the long-term behavior of a graph. There's a lot of different techniques, but we didn't have like a technique for specifically finding the local max and min of a graph. So that's where this is leading up to. It's just a little bit more precision in graphing and curve sketching. So let I be the domain of a function. F of c is a relative minimum if there exists an I within the open interval I1 containing c such f of c is less than all f of x, all nearby f of x, right? So a relative minimum, graphically speaking, all that is the bottom of a valley, right? We say it's a minimum if f of c is less than all nearby f of x for all x in that open interval I1. And then we say that f of c is a relative max if f of c is larger than all nearby y values for all x in that open interval. This is a little bit of jargon. I feel like when we work a few examples, I feel like it'll sink in a little bit more. And again, that's just the relative max is just the peak of a mountain. If a function f has a relative extreme of value f of c on an open interval, then c is a critical value and f prime of c equals 0 or it does not exist, right? So what we're doing is building a case for finding specifically the peaks of the mountains or the bottom of the valleys, right? And remember, when the first derivative is negative, that means your original function is decreasing. When the first derivative is positive, your original function is increasing, right? So we're gonna let's see how this unfolds or how we use this to find specifically, the critical values, the relative extrema, either the max, the local max, or the local min, right? Let's see how this unfolds. I'm trying to get to an example. They keep I keep hoping it's like, oh, where's my example? The first derivative test for relative. Okay, yes. So the first derivative test for relative extrema for any continuous function f that has exactly one critical value c in an open interval ab, f has a relative minimum at c if f prime of x is less than 0 on the left side of c, and f prime of x is positive on the right side of c, right? So we have some interval, and c is somewhere in the interval, and c is a critical value, which means the derivative is 0 at c. Then if we choose a test point on the left of c, and if the derivative is negative, that means the original function is decreasing. If we choose a test point on the right side of c, and the derivative is positive, that means the original function is increasing. So if our function goes from decreasing to increasing, that implies that c is a relative minimum, right? So that's the first derivative test. We can use the first derivative to see if our original function is increasing or decreasing on either side of this critical value, and then that tells us whether we have a relative max or relative min. Now, I feel like that's a mouthful. Again, I'm trying to get to an example. Let me see. And the relative max statement here is reiterating what we just said in the previous. You just have to adjust the concept for a maximum instead of a minimum. And then we say that f has neither a relative max nor a relative min if f prime has the same sign on either side of our critical value, right? So if it goes from increasing to increasing, then it's neither, or if it goes from decreasing to decreasing, it's neither a relative max nor a relative min, right? So what we need to identify a relative max or a relative min, we need a sign change in the derivative. You know, we'll see it. I'm trying to get to an example. Okay, this is like a pictorial representation of what's going on. Let me grab my pen. I'll give people 5 more minutes to get into the waiting room, and then I'll let them in. So, like, for instance, here. So it says the graph over the open interval AB. So C is our critical value. The derivative, right, the slope of the tangent line there should be 0. And then if we choose a test point on the left of C and we get a negative result in the derivative, the original function is decreasing. If the derivative is positive on the right side of C, then the original function is increasing. So if our function goes from decreasing to increasing, that means we're working with a relative minimum value, all right? To go from decreasing to increasing. So again, on the left side of C, the derivative was negative. On the right side of C, the derivative was positive. And then for a relative max, just, you know, it kind of flips. If this is our C, on the left, the function is going to be increasing. And then on the right, the original function is going to be decreasing. So if our function goes from increasing to decreasing, that means we're working with a relative max. Okay. And then these are examples where there are no extrema. Like if C is our candidate for our critical value, and the original function is decreasing on the left and decreasing on the right, then there's no relative max or min. And we just said it is decreasing over the entire interval. And then it's similar if it's increasing on both sides. So we need the derivative to have a sign change in order to have a relative max or a relative min. Okay, let's give this one a go. Oh, I might need some space. Graph the function f given by this and find the relative extrema. Okay, yeah, let me give myself some space. I kind of want to let the gentleman in, but I think our agreement was the 15-minute mark. So I'm looking for that. This is slide 14. Come back up. Come on, you can do it. There you go. Copy. Now I'm going to try to keep this as simple as possible. The techniques that I'm going to use here are simple, and you know how to do them. But the pitfall is where a lot of students get lost is because it's information overload. So I'll try to be as organized as best I can. Just try to absorb what you can, but don't get lost in like what I'm doing. It's and like for instance. So let me start by getting a copy of this guy. So we have this f of x, 2x cubed, 3x squared, 12x plus 12. Okay. Copy. Paste. Okay. So we want to graph this out, right? So there are a few things that I look for when I'm graphing. So like one, I like to start with my intercepts. I think that's good. Okay. And we'll expand on that. Let me see. We'll look at the derivative. Let me think. We can do our critical values or potential critical values. We could do a test for symmetry. And then I'm going to say a few additional points. And there might be some more things we can add to this, but this will be good. This will be a good starting point. A few additional points. And then lastly, we're going to graph it or put it all together. Okay. So let's start off with the first one. And I think I'm going to shrink this down and just use this as a reference. Okay, so I just kind of keep it there. So let's start off by looking at our intercepts. So, you know, I personally like to start off with the y-intercept. I find that that's oftentimes easier. And to find the y-intercept, we set x equal to 0. Okay. So if we set x to 0, then you can quickly see that the y-intercept is 12. Okay. Then let's go ahead and explore the x-intercept. Now, let me see. That one we would have to set y to 0. It looks like we'd have to do factor by grouping. Let me see. We could factor out. I don't know that we can get this by factor by grouping. I might just bypass the x-intercept for right now. I could switch those around. I'm going to bypass it for right now, just because I don't think it's a simple result. We can come back to that. I'm trying to keep it simple, so I'm going to just put a pin in that part. Let's look at the derivative, though. I think that's the main thing that they want us to do. So I'm going to come back to the x-intercept, just for the sake of keeping it moving. But I'm going to move on to the critical values, potential critical values, and I'll keep working over here. Okay, so if we have our f of x, let's go ahead and pull a copy. Let me check on guys one more time before I go forward. So it's a good amount. Okay, let me go like this. Get this gentleman in here. Okay, that's fine. These names are similar. Okay. All right. Let me just check my number or confirm my number. I got 18. So that's correct. Okay. All right, let me go back to sharing my screen. Okay, that's looking good. All right. So, and we're kind of just getting started. And so this is example 1, and we were tasked with graphing this polynomial. And we kind of made a mini playbook on the left here. That's what this little reference guide is here. We found the y-intercept, and we decided to just skip the x-intercept, because the x-intercept looked like it was going to be a little bit involved. Sorry, it's not simple. So I put a pin in that. We're going to come back to that part. But then so we're starting off with critical values. In other words, we're going to look at the first derivative, right? So if we take the derivative, right, we're taking the derivative of this guy. What is that? A 6x squared minus 9. Wait a minute. Something's not right. That's supposed to be squared, right? Yeah. Right here. That's supposed to be squared. Okay. Okay, so then that makes that what, 6x minus 12. Okay, so that's the first derivative. So then our critical values are going to occur when either the derivative is either 0 or undefined, right? So what we're going to do is set the derivative to 0 and solve, okay? So we're going to set the derivative to 0 and solve. Now this guy, I think we can factor it, right? We could potentially factor it into some form like this. Now maybe we can factor out, it looks like we can factor out 6 from all the terms initially, okay? I think I need to write it, so let me get rid of this. If we factor out 6, then we're going to be left with x squared minus x minus 2. Now let's factor this guy. Let me see, x and x. Because the second sign is negative, our sign should be opposite. So one needs to be positive, one needs to be negative. It looks like it's a -2 and a +1. Okay. Okay. I mean, I guess it would have worked. We could have tried it, but I didn't want to waste a lot of energy on that. Okay. So we were able to factor the derivatives, our candidates for potential critical values. If we go ahead and solve this, from here we get what? X equals -1 or 2. So what we're saying is that these are candidates to potentially be either a local max or a local min, right? So now we're going to use the first derivative test to see, okay, how does the function behave on either side of these potential critical values, right? So here's my number line. Here's my positive x in this direction. Here's -1, and here's 2. So when we evaluate these guys in f prime of x, let me move this guy. I'm gonna move it up here. No, I think we'll be has fun. When we evaluate these guys in f prime of x, I think they both give us 0 in the first derivative, right? So then if I choose a number on the left side of -1, like for instance, if we plug in -2, does it make the first derivative positive or negative? Let's see. So if we plug in -2, this result is going to be negative. This is positive over here. We plug in -2, this is negative here. So double negative looks like ultimately our result there is going to be positive. Okay. So we get a positive result here, which means our original function is increasing on that interval. On the left side of -1, the original function should be increasing. Okay. And it looks like we still might need to come back and find the x-intercept. And I'm going to try some things there. Like I said, I wanted to just save it for a little bit later. Let's choose a test value between -1 and 2. Now, I think that we already chose x equal to 0, and we got a positive result. Oh, so that might be the case. All right. So if we choose a number between -1 and 2 and plug it into the derivative. Matter of fact, wait a minute. Wait, before I do that, let me just do it. So if we plug 0 into the first derivative, we get a negative result, right? So we got to fix that. So, and what I did is here. If I plug 0 into the first derivative, this term goes to 0, this term goes to 0, and we're left with the negative result. Okay. So then in the first derivative, we got a negative here. So what we're saying is that the original function should be decreasing between these potential critical, between -1 and 2, the original function should be decreasing. Okay. So then let's choose a test value on the right side of 2. Let's maybe like when x is 3. So if we plug in 3, here we have a positive. Here I think we have what? A positive. Here we have a positive, right? So if we plug in any number that we plug to the right of 2 into the first derivative, we should get a positive result, which implies that the original function is increasing. So it looks like on either side of these critical values, the function is increasing. Sorry. The function is increasing on the left side of that guy and then decreasing between these two guys and then increasing, right? So for that critical value of -1, it looks like that's a local max. Okay, so I'm going to say relative max. And then this one would be a relative minimum. Okay. If we wanted to do a test for symmetry, we would replace x with -x and then see if we can get the original or a negative times the original. I don't think it has any symmetry. And then for the few additional points, usually what I do is like I take either my vertical asymptotes or my x-intercepts. So we would need the x-intercepts. But honestly, we could choose points between these guys and it'll be okay for now. The x-intercepts will be nice, but I think there'll be a little bit extra for this example. But we can still find a few additional points between and beyond all of our critical values, and that'll give us just a better sense, right? I'm thinking about like factor by grouping. I'm just trying something. We could factor out a 3 from those guys. It might be able to be factored. I just didn't want to spend a lot of time on that. Okay, so let's put all this together. Let's put what we have together. Let's duplicate and clear. Okay. All right. So let me see. Our x values, we didn't get our x-intercepts, but we got critical values, and we'll find those corresponding y's, -1 and 2. When x is -1 into the original, it's like a -2, -3 is a -5. It's a 7, so like 19, like 20. So maybe if we go in like 30, what about when we plug in 2? 8 times 2 is 16, minus 12 is 4, minus 24 is -20, so -8. I think if we go like 25 on the y-axis and on the x, we need to just go to like 3. Okay, so I was just trying to get a sense of the window. So for let's do right here like this space. So this persists, and this will be our graph paper. Let me see. Is this it? Come on. Okay. Yeah, okay. That's already set. Okay. All right. So let's try to put all this together. So let's see. We're going to let this be our positive x direction. Okay. And we'll go y, positive y in this direction. Okay. Let's move this way some. That looks decent. Okay, I think X we felt like we needed to go to maybe like 3 or 4, maybe 5, something like that. So I'm gonna go 1, 2, 3, 4, 5. That should be good on the X. So origin, these went by ones. Okay. On the Y's, I think we needed to get to like maybe 25 or 30. Let me see. 5, 10, 15, 20, 25, 30. That should be good. 10, 15, 20, 25, 30. So these are going by 5s. These are negative. Okay. All right, so we got some graphics. Now we did get our wireness up. We got a wireness up to 12, so I'm going to go ahead and graph that. Let me see. Halfway would be 12.5, so about right there. That's the order pair 0, 12. We just bypass the x-intercepts just for the sake of simplicity. Okay, we got these critical values when x is -1 and when x is 2. All right, so we need to find the value. We need to find those actual points. We do have that a max occurs when x is -1 and a min occurs when x is 2, but we need to find those corresponding y's to get the actual value. So we're just gonna, I guess I could just do it manually. Let me see. When x is -1, the first, let me see, we get a -2 minus 3 is -5 plus 12 is 7. So I think that's 19. So when x is -1, the corresponding y is 19. -1 and 19 is here. Okay. And then when x is 2, 8 times 2 is 16. 16 minus 12 is what, 4? So then that's 4 minus 24 is -20, plus 12 is a -8. So 2, -8 is about here. Okay. So we know that's the max and the min. We have our wire intercept. Okay. It would be nice if we had our x-intercepts, but it's going to be a rough sketch from here on out. We could choose a few additional points, right? Like I don't know that I'm gonna do it just for the sake of time, but like we have our critical value, so we might choose like, okay, let x be -2. I don't think we had any symmetry, so let x be -2, -3. Let x be 1, 3, and 4, and then just plot those points. I'm just going to do a rough sketch, so it's going to be a little bit off, but the gist of it, so we get something like this. Now my x-intercept is off because I didn't try to find it. It passes through that, passes through this. So this is just a rough sketch. Right now, if I wanted to be more precise, I can go back and actually find those x-intercepts and we can plot those. Or if we had just at least chose a few additional points. Let x be -2, let x be -3, let x be -4, let x be 1, 3, and 4. Find the corresponding y, plot the points. That'll be everything. Again, I'm just trying to be a little bit quick because these can kind of take up a good amount of time. All right, if you're not careful. Let me show you. I think if I can go like this. Nope, get out of that, please, and thank you. Come on. No. Let me see this one. All right. Like that? Nope. Nope. Want this? It's not showing me my options. Maybe it had to be like this, and then click this. No. Sorry, guys, I'm coming. I'm just trying to get this to behave. And it's not showing me everything. Let's see. Come on. That's what I really didn't want to do. But it is behaving better. With the colors. So it's, oh no. We're going to undo whatever we did. Oh my goodness, there it is. I need you to behave. What if I go like this? And then I do this. Okay. Well, I had to distort it, but that's fine. And then I could just put it back maybe. Okay. So we get an image sort of like this, right? Again, if we wanted more precision, we could have chose several values of X, find the corresponding Ys. And we have other techniques for finding the X-intercept, but I just bypassed that for now to keep it light. So, when we did it by hand, we got an image like this. Now let's see what the text says. So we want to graph this function and find a relative extreme. Suppose that we are trying to graph this function but do not know any calculus. What can we do? We can plot a few points and determine in which direction the graph seems to be turning. So they just chose several values of X, find the corresponding Y, and they got the same max and mins. And see, that's what we were saying, right? Choose several values of X, find the corresponding Y, plot them, and we'll get in them. And we would have got the same thing. Okay. Now we can see some features. Let me see. Find a general expression for the derivative. So that's what we did. Determine whether the derivative does not exist or where it's zero. So I think that's what we did. We did that already. So we got 2 and -1. So then the 2 and the -1 break the number line up into 3 sections or 3 regions, A, B, and C. So then we had to do the first derivative test. We choose test points like we did, right? So we chose like when X was -2, plug it into the first derivative. I think we got a positive result because we got increasing, right? Here, when we chose when X was 0, we almost made a mistake there, but we caught it. When we plug 0 into the first derivative, we got a negative result, which means the original function was decreasing on region B. And then we chose something to the right of 2. Now I think we chose 3, they chose 4. The whole point is the derivative on the right side of 2, all those results are going to be positive, which means our original function is increasing on region C. So we're saying that the original function goes from increasing to decreasing and then back to increasing. So then that identified our max and our min, right? We had a relative max when X was -1, the corresponding Y was 19. And then we had a relative min when X was 2 and the corresponding Y was -8. So we had our max and our min. Yeah, we just kind of put all the images together. But again, they graphed theirs by just plotting points, right? So that's another, and we mentioned it, we just didn't do it for the sake of time. I feel like there should be questions. We really do need to kind of go into the next section, but I think I'm gonna just kind of keep going and take my time. Let me see, find the relative extrema for this function given by this and then sketch the graph. We'll find the extrema. Let's find the extrema. Let's just kind of go ahead and do that. And we'll kind of go from there. So if we want the extrema, we were given this f of x. Let's look at the derivative. Okay. So now we're going to take the derivative of what the power comes down, -2. We subtract 1 from the power. It's going to give us a -1/3. And I think that's it. Because if we say times the derivative of the inside function, it's going to be times 1. And the derivative of a constant is 0. All right. So then the critical value is going to occur when the derivative is either 0 or undefined. Now, keep in mind, this guy is, if it has a negative power, that's going to be the cube root of x minus 2. We got a 3 here and a 2 here. Okay. So I don't know that we can find it because basically a fraction is going to be 0 when the numerator is 0, right? So I don't think we can find an x that makes it 0, but we might be able to find an x that makes this undefined. Let me see. So if x is 2, right? Because if we plug in when x is 2, 2 minus 2 is going to give us 0. So then that's going to give us 0 in the denominator, right? So our critical value is when x is 2, right? And we want to evaluate the function, the first derivative on either side of this potential critical value, right? This makes the derivative undefined, right? So let's test something on the left side of 2. All right, let's try when x is 1. Cube root of -1 is going to be what? -1. We get a negative result there, right? So we get that the first derivative is negative on the left side of 2. So that implies that the original function is decreasing. On the right side of 2, maybe something like 3, we get a positive result. The derivative is positive. So that implies that the original function is increasing, right? So if our function goes from decreasing to increasing, then this should be what? A relative minimum value when x is 2. Okay. Another point that's usually pretty easy to find, again, is the y-intercept. So if we let x be 0, I'm thinking we're gonna get, like, you can find the number. It's not gonna be a clean number. I would say just like choose several values, just choose a few additional points and plot them. And we just want to be sure to get this relative minimum value. So like when x is 2 into the original, it looks like we get a value of 1, positive 1, right? So then and this is just a rough sketch. And again, what you can do on your end, once you have that critical value and you've confirmed using the first derivative test, whether it's either a relative max or relative min, just choose a few additional values of x, find the corresponding y, and plot the points. And that'll be a good place to start without all the extra stuff, right? But we said that when x was 2, we plugged into the original and we got, let me check it again. I think we got a value of 1. 2, 1. Is there any symmetry? I don't think there's symmetry. So we get this point here. We should choose some values. I'm just not doing. I'm just avoiding. I could, like, put it in the graphing calculator, like when x is 1, when x is 0, when x is -1, when x is 2, find the corresponding y. Again, I'm just avoiding it for the sake of time. But that should be the whole point. Oh, we said minimum, right? Do we have a horizontal asymptote? I feel like there's a horizontal asymptote. But that should be a minimum value, right? So let's see. First, find the derivative. I think we got the derivative. Okay. So therefore, x equals 2 is the only critical value. And then we got that it went from decreasing to increasing. So that means that there's a relative minimum occurs when x is 2. Okay. So that's a relative minimum. And then just choose a few additional points. Again, I would just choose a few values of x, find the corresponding y, plot the points, and that'll suffice. Okay. So yeah, and that's what they did. They chose several values of x, and I just wasn't doing it for the sake of time. Now we could either just generate the graph with the graphing utility. In our TI-83, now we can generate this table rapidly. We can like make a table and use that to plot the points. Maybe I'll do that for another one, because we are a little bit past halfway of this section, but we do need to move on. Okay. So we got it. Let's let that be. Let's see what else we got. Okay, let me go like this. Oh, we're actually almost there with all these quick checks. Let's see, find any relative extrema and then sketch the graph of the function given by this. Okay, let's give this one a go. I think we can get it based on the way that they were doing the previous. I'm just going to start off with the potential critical values. Okay. So first, I'm going to start with g prime of x. Looks like we got to use the product rule. So the first times the derivative of the second times what? -1. So the first times the derivative of the second plus the second times the derivative of the first. Okay. Let's see if we can simplify this down. It looks like we can factor out x e to the negative x from both terms. Let me see. It looks like we can factor out x e to the negative x. And it looks like we're left with one term is 2. I'm going to say minus x. Okay. So then for our critical value is going to occur when this guy is either 0 or undefined. Right? So one thing we can do is set it to 0 and solve. We'll get x equals 0. I don't think that one will ever be 0. Nor will it ever be undefined. Right? And then, so no result from that middle term or middle factor, but then that third factor, I think when x is 2. Yeah, I think we're okay. All right. So these are the potential critical values that we get from setting this denominator equal to 0. Okay. So then these two critical values break the number line up into 3 regions. Here's 0, here's 2. Actually, I need more space in this. I'll just work here. So if we consider f prime, these guys are both zeros in the first derivative. Okay. So again, we have a region like A, region B, and region C. So if I choose a point in region A, something like -1, and I want to test it in the first derivative or use my first derivative test, let me see, that's negative. That's going to be positive. That's positive. It looks like we're going to have a negative times a positive times a positive. It looks like the original was ultimately negative here, which implies that the original function is decreasing in region A. A number in region B is something like when x is 1. Looks like we get a positive, and a positive. So that means the final result there is going to be positive, which implies that our original function is increasing. And then in region C, something like 3, when x is 3. We get a positive, and a negative. So ultimately, a positive times a negative is ultimately negative. So that implies that our original function is decreasing. So if this is correct, going from decreasing to increasing implies what? A relative minimum value here, and then a relative maximum value here. It looks like it passes through the origin. Because when x is 0, I was like, well, let me look at my y-intercept. When x is 0, we get 0 times 1, which is just 0. So it looks like it passes through the origin. Okay, let me see. So again, we could just choose a few additional points. Let me show you one way, like at least, we gotta, and then for this max and min, I think one of them is the origin, right? So we have a relative minimum value at the origin, and then when x is 2, you get what, like 4 over e squared, whatever that number is. You would need your calculator for that. So where's this one? Okay, let's reload and refresh. Come on. Okay. So, I mean, obviously you can just use the graphing utility. I just want to show you how to generate a table of values quickly. This is using a TI-83 plus. So if I go to my y equals, and I go to x squared times e to the power of a negative x, okay? Let me see. I'm going to quit. I'm going to go to table set, so it's like hitting second window. I want my table to start at like negative. Let's start at -3. Okay. And then table is just above graph, so I'm gonna hit second graph to get to the table. That way it captures when x is 0. I think we got the origin, we got that point. And then when x was 2, we got some weird decimal, right? But you can see it quickly generates a table. So what is that that's 180. So obviously we wouldn't use x is -3. -2 is pretty much 30. All right, so -2, 30, -1, 2 point something, then to the origin. Let's do a rough sketch since we can. I kind of want to shrink this down. Come on. Come on. So again, we're doing what we can together. You're gonna have to rely on my pre-recorded lectures for this, just because we're short on time. So then a rough sketch using those points. Here's our positive x. Here's our positive y. Let me see. 2. See a few more in this direction. Oh, it's behaving like exponentially. Okay, so it's tending to 0. Okay. Right here. Let me see. So it seems like we still have like exponential something or another. Come on. My device is like throwing a tantrum. Let me see. So we have a relative min, a relative max, and it still looks like it's tending to 0. So I know we have this point here at the origin. When x is 2, we're at like a half. So it's about here. So it looks like it's behaving something like this, like that, and then it's like tapering off. I think it's something like that. Because 2 is a relative max. And then the rest of these get closer and closer and closer to 0 as we go off to the right. And as we go off to the left, it tends to infinity. Okay, so I get something like this. Let's get rid of this, and let's just see what the text says. Come on. Please. Oh, there we go. Okay, let's see what it says. And I think this is the last one for this section. So let me see. To find the critical values, first we find G prime. Where's the negative? Okay, I think they just wrote it a little different, but we got the same thing. No, we got the exact same thing. Yeah. Okay. So then now we need to find when G prime is 0 or where it does not exist. We got 2 values, 0 and 2, correct. So it breaks the number line up into 3 regions. We got it went from decreasing to increasing to decreasing. I think we're okay. Let's keep going. By the first derivative test, so we got a relative minimum at the origin, and then a relative max when x is 2. And that's exactly the image that we got. That's so interesting. All right, and again, we just chose several values. Like once we had our relative max and min, then we just chose a few additional points and then just connected them with the smooth curve. Okay, that was interesting. All right, so we have a solid 20 minutes. I do want to take some time to go into the next section. Let me go ahead and make a copy of this available. Share, come on. It's like totally dragging today. Come on. Thank you. Spring, traditional calculus notes, updated daily. All right. So let's send this one there, and let's just kind of do our best with 3.2. Yeah, let's look at it. Come on. Okay. So let's give this one a go. Let's change the view. Single. Okay. All All right, so we continue chapter 3 on some applications of the derivative. And so now we're going to look at 3.2 using the second derivative to find max and min values in sketch graph, right? I kind of wanted to bring this up in the last one, but I didn't because it wasn't time for it, right? A few objectives here are to classify the relative extreme of a function using the second derivative test, and then graph a continuous function in a manner that shows concavity, right? So I'll just kind of summarize it here. So we use the first derivative to kind of identify our potential max and min values, right? So we had our potential critical values, and then we used the first derivative to determine how the function was behaving on either side. Well, the first derivative tells us whether a function is increasing or decreasing. The second derivative tells us if our function is either concave up or concave down, right? If you think about like a cup and the curve of our function, the second derivative tells us whether the cup is opening downward, that means the second derivative is negative, or if the second derivative is positive, that means the cup is opening upward, right? So if we have our critical value where the first derivative is either 0 or undefined, and say the second derivative is negative, which means the cup opens downward, that means that our critical value is sitting at the peak of a mountain. So it should be a maximum value, right? You can use a second derivative in conjunction with the first derivative, to identify your local max and mins, right? Suppose that f is a function whose derivative exists at every point on the open interval I, then f is concave up on I if f prime is increasing over the interval, right? And f is concave down on I if f prime is decreasing over the interval, right? So concave up, the second derivative is positive. Concave down, the second derivative is negative. If the second derivative is positive on the interval I, then the graph is concave up. That means f prime is increasing over the interval, so it's turning up. If f double prime is negative on the open interval I, then the graph of f is concave down. All right, so the f prime is decreasing, so the function is turning down on I. I don't know. Let's back out and open it up again. Okay, so suppose that f is differentiable for every x on an open interval, and that there's a critical value c on that interval where the f prime is 0. Then f of c is a relative min if the second derivative is positive, right? If it's concave up and we have a critical value, that means it's sitting at the bottom of a valley, so it's a minimum. If f of c is a relative max, it's if the second derivative is negative. That means we have concave down, which means our critical value is sitting at the peak of a mountain. If the second derivative is 0, then we use the first derivative test to determine whether f of c is a relative extreme or not. So we can't always use the second derivative test. When that fails, then we just revert back to the first derivative test. So here we're asked to graph of the function given by this and find the relevant extrema. Let's start by finding our first derivative and second derivative. So our first derivative, 3x squared plus 6x minus 9. And then our second derivative, 6x plus 6. Can we factor that guy? That would be nice if we could. But I feel like that's going to be extra work. So I'm not going to do that right now. And plus, I don't think it factors that easily. Okay, so I'm going to let that be. Okay. So let's find our potential critical values by setting the first derivative to 0. I don't think it won't be undefined anywhere, but we might be able to find a 0. Okay. It looks like we can factor out a 3 from all of those terms. X squared plus 2x minus 3. And then maybe we can take this a little bit further. One's plus and one's minus. Positive 3 and a negative 1. Okay. So that gives us our candidates for the critical values. I'll kind of work here. Let's do like this. Oh, redo. Wait a minute. Oh no. And that was a 1. So from our factorization, we got what, -3 and 1. So -3 and 1 are our candidates for our critical values. And we're going to evaluate them at the first derivative, and we're going to evaluate them at the second derivative. Both of these two gives us information about the original graph. So these both make the first derivative 0. So this makes the first derivative 0. This makes the first derivative 0. So let's go ahead and use the second derivative test to determine whether these are max and min. Now we could use the first derivative test like we did before, and that would be fine. So if we plug in -3 into the second derivative, it looks like we get a negative result. All right. So -3 is negative in the second derivative, which implies that the original function is concave down, which means that we have what, a relative max. Okay. What happens if we plug 1 into the second derivative? It looks like we get a positive result, which implies that the original function is concave up, which means that this would be a relative minimum value. Okay. And then again, just a few additional points, maybe make a table, choose some x values, find the corresponding y. I'll just do it quickly in my graphing calculator since we can. So we got x to the power of 3 plus 3x squared minus 9x minus 13. Okay. I think the table that we have should be fine. And we need to go up to like -4. Okay. So if we were to do a rough sketch, say this is my positive x in this direction. Say this is my positive y in this direction. Okay. Let's see. Our x values, maybe if we go like from -4 to about 3 or so. Let me move this over. So like if we did 1, 2, 3, 4, 1, 2, 3, 4, 5. Origin. And then our y values on this window, maybe like 20. Yeah, it looks like we need to get to at least 20. So maybe 20 or 25, maybe 30. Let me see. 5, 10, 15, 20, 25, 30, 35. 5, 10, 15, 20, 25, 30. 25, 30. These are negative. 5, 10, 15, 20, 25, 30, 35. Okay. So then let me see. So I want to kind of start with my extrema. So when x is 0, y is -13. So that's about here. That's a maximum value. Okay. Another one we had was what? Sorry, I think I did that wrong. Let me back up. When x is -3, right? When x is -3, we get a max at 14. So -3, 14 is about here. Okay. When x is 1, we get a y value of -18. So that's about here. Okay. And then just a few additional points. For instance, when x is 0, we're at -13. Kind of run out of space here. 0, -13. X is -1, we're at 2. 2 is about like here. Might as well do -2 and 9 is about here. We know that should be a max, so I'm gonna label it, or let's say relative max, and we'll say relative min. Okay. When x is -4, we're at 7. So that's about here. Let's just go ahead and do -5 is -18 is here. And then like when x is 2, got to get you guys out of here. 2, 11, no, 2, -11. Like here. And then let's do 3. 3, 14 is about here. Okay. So then if we connect these with the smooth curve, something like that. But we have identified our max and our min, and then we just plotted a few additional points. A little bit weird, but that's okay. Let's see. So first find the first derivative and second derivative. So I think we did that. Then we got our critical values of -3 and 1. Then we use the second derivative to identify the relative max and relative min. Then by calculating and plotting a few more points, we can make a sketch as shown below. All right, so all the text did, found the relative max and the min, and then plotted some points, and that was it. Now there's more to that narrative, but like if we try to calculate these intercepts, these examples are going to be like, we'd have to use some other method for finding the intercepts as opposed to like things that we talked about in college algebra. And I think we will explore it, but just for the sake of simplicity, for right now, we're just concerned with the extrema and then a few additional points. That seems to be what's going on. Okay. Let me kind of scan real quick. We can hang out for like another 5 or 10 minutes. So again, we're looking at the first derivative and the second derivative. Let's at least go ahead and calculate the derivatives. So then K prime, the derivative of E is itself times the derivative of the power. So this is going to be times 2. Minus the derivative of E is itself. And the derivative of that power is just going to be 1. So then let's look at K double prime. The derivative of E is itself. And times the derivative of power, then it's just going to become a 4 now. And then this kind of repeats. So then our potential critical values occur when the first derivative is 0. We could factor out an e to the x. If we factor out an e to the x, does that help us? So we should have 2e to the x minus 1. So we set this guy to 0 and solve. I don't think that e to the x will ever be 0, so there's no result for the first one. But the second one, I think we can get a result. The second factor. So if we, let me see, add 1 and divide by 2, e to the x equals 1/2. So x is going to be equal to natural log of 1/2. So that's our only critical value, whatever that number is. Then if we plug this into the second derivative, let me see. So 2 times that, let me see. So when we evaluate K double prime of natural log of 1/2, it's going to be what, 1/4? So we're going to have 4e to the natural log of 1/4 minus e to the natural log of 1/2. Right? So then this should cancel this. The first term looks like it's just a 1. Second term is 1/2. We finish with 1/2, which is a positive result. So we got our potential critical value, whatever this number is. And then when we plug that number into the second derivative, we get a positive result, which means that our function is concave up. So that means that this would be a relative minimum value, right, by the second derivative test. So then we crunch that number and then we plug it into the original. If we plug this into the original, let me see. I think we get what, a quarter there, 1/4, a quarter minus a half sounds like it's a negative 1/4. So then the ordered pair will be a natural log of 0.5, comma negative 1/4, right? So anyway, we found the x value. We just plug this into the original to find the corresponding y, and then plot a few additional points and call it a day. We found the first derivative. I think we got both of those results. And then, yeah. So we only had the one critical value of natural log of 0.5. And then we use the second derivative test. We got a positive result, right? So then that means it's a relative min. And then we take that x value, plug it into the original to find the corresponding y. And I think that's what we got. We said natural log of a half, comma, a negative 1/4. And then plot that point with a few additional points. And we get this. Let me see. Let me just do a quick scan. So if you want to see more of this, you have to use my recordings. Let me see. So a point of inflection, that's where our graph goes from concave up to concave down, right? So when we have our second derivative, let me see the critical value for that. So the critical value for the inflection point is going to occur where the second derivative is either 0 or does not exist. So when you're looking at the second derivative, if you set it to 0, you have a candidate for a point of inflection, either when the second derivative is 0 or does not exist, and then you choose test values on either side. And as long as you get opposing signs, like if it goes from positive to negative or vice versa, then you have a point of inflection. And the point of inflection is where the graph goes from either concave up to concave down, or it goes from concave down to concave up. Again, those details, I'm going to have to refer you to my recording. Okay, and let me kind of scan this one as well. This gives us an overview of a strategy for sketching graphs, because it's a little bit different than what I was originally going to do, but I'm going to just kind of glance at it here. So if we're going to sketch a curve, I know the battery's low. First, we look at our derivatives in the domain. So find f prime and f double prime, and then make a note of the domain if you can. Then we have find the critical values by solving f prime equal to 0 and where it does not exist. And then find the function values at these points. So we want to determine if the original function is increasing or decreasing based on these potential critical values. We can either use the first derivative test or the second derivative test. And then also we want to do a search for points of inflection. That's where the graph goes from concave up to concave down. So we just explore the second derivative. The critical value there comes from, we set the second derivative to 0 or where it does not exist. And then we gotta do a few test points on either side into the second derivative to see how the sign behaves. Okay. And then sketch the graph. Okay. So all they're doing, they're just evaluating the first derivative and the second derivative. The first derivative tells us about increasing, decreasing, and relative max and relative min. Second derivative tells us about whether it's concave up or concave down and points of inflection. All they're really doing is exploring the first derivative and second derivative. And so we'll get our critical values from there. And then once we have our critical values, just find a few additional points between and beyond all of your critical values, and then put it all together. Relative max, relative min, point of inflection, few additional points. Any intercepts that you can find relatively easily, don't go too much. Like y-intercept is oftentimes simple, but the x-intercept can be a bit much. So that's why I kept skipping the x-intercept, because they didn't really intend us to find those x-intercepts. But long story short, overview of sketching for this purpose, we're just exploring the information that comes out of the first derivative and the second derivative with the few additional points that we choose between and beyond all of the critical values. And we put it all together. I would love to do this one right now, but we are out of time. I'm going to have to leave this for you. But that was informative. Just trying to see if there's anything else I need to mention. Okay, so that was the meat and potatoes, right? So you still have practice, and you'll get plenty of practice in like the homework. But the main takeaway from these first two sections of chapter 3, we're exploring some applications of the first derivative for curve sketching, or the first derivative and second derivative, right? First derivative tells us whether the original function is increasing or decreasing. We can also use it to identify relative max and min, so we explore some there. And then the second derivative tells us whether the original function is concave up or concave down, right? So we can use the second derivative to identify your relative max or min once you identified your critical value. And then the second derivative also tells us about points of inflection, right? And so that the critical value there comes from whether the second derivative is either 0 or does not exist. And then you just need to verify a sign change on either side of the second derivative for that, okay? So that's about the best I can do for summarizing that. It's going to take practice. As long as you're like, you can like be comfortable or somewhat confident in taking a derivative, then it just takes a little bit of exposure and practice and prodding and digging to kind of get down, okay, well, what does that mean about the original? First derivative tells us increasing or decreasing. Second derivative tells us about concave up or concave down. With that, we are out of time. Are there any burning questions? I feel like there should be, but I totally get it if I know that feeling. Let me just kind of open the floor for any burning questions before we go our separate ways. And while you guys think about that, I just want to make this available. Okay. And again, I just did a quick scan while we were together. If you want to see more details on this presentation, then you have to use my pre-recorded lecture. Otherwise, you have access to the homework. I'll be updating your grades probably within a week or so. I have something else I need to do before it, so that's kind of like the hold up. But aside from that, okay. So if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening, and we'll meet back on Wednesday to explore the next two sections. Now, you don't have to wait on me. If you get to some level of confidence with these first two sections, if you have time and you just feel like you can do it, I'd encourage you to go ahead and look at the recordings for sections 3.3 and 3.4 as well. So that way, when we get in class on Wednesday, idealistically, you want that to be a review, right? And idealistically, when we get in class at any time going forward, it's best if you look at it in advance. So that way it's a review when we're together versus, trying to play catch up, if at all possible. All right, gentlemen, enjoy your evening, and I'm available if you need support or help with anything. All right, guys, take care. All right. Glad I went with my intuition and didn't try to find the X. I was like, I don't think we're supposed to find the X thing there. All right, I got to get ready for my next class. Stop. Come on. Okay, you guys look good there. Let me check here. Ooh, glad I checked. So I'll go ahead and get this gentleman right here. Evans. Hold on. For two gentlemen that just led into the room, I went on to give you attendance credit because I saw you waiting. I just saw you just now. You got attendance credit. You'd have to use either the recordings. It's two different versions of this presentation. We did what we did live today, which is just in our regular playlist, or you can use my recording from the past. Either one should suffice. All right, gentlemen, enjoy the rest of your